So Monty is off doing, I have no clue what he's doing, he's somewhere. So I'm going to be your substitute for today and Wednesday. So a word of warning for you guys, I am not an engineer, I am a mathematician. So today and Wednesday I'm going to teach you about 4 semesters worth of graduate math in 2 days. So we're going to see how this goes, and if you're not thoroughly confused after this slide, then I did something wrong. So another thing to keep you guys in mind, I'm bad at slides because I go too fast when I just read slides because I don't have to write anything down. So yell at me to slow down, yell at me to ask questions, whatever, because we're going to go at warp speed today and Wednesday. So today's topic is going to be on matrix groups. So in essence, we're going to learn how to do calculus with matrices. It's going to be a little bit more involved than that, but that's the crux. And the important part from today isn't so much that you guys can regurgitate formulas, but it's more important that you have a vague understanding of what the stuff means. So with that, let's start. So this is a list of books that Monty put together for you guys to go through because, of course, an hour and a half of me talking is not going to teach you, something that has 1,000 textbooks written on it. So these are things for future reading. Of course, if you just Google Lie groups, Lie algebras, matrix groups, whatever, learn it from more than just me. So a matrix group is just a group of invertible matrices. So there's 3 things in this sentence that's important. There's the word group, there's the word invertible, and there's the word matrices. So I'm assuming everyone knows what an invertible matrix is, right? It's just a matrix that you can multiply by something else and get back the identity. But I'm assuming that not everyone in this room knows what a group is. Is that correct? Okay. So a group isn't, we'll get that in the next slide. So, of course, a couple reasons to study these things is the study of Lie groups or matrix groups or whatever you want to call them are ubiquitous in all sorts of areas. We're, of course, going to use them for robot tracking and position orientation garbage of sorts, but it's used much more often than that. And one thing I want to keep in mind is it's also useful in Riemannian geometry, whereas instead of doing calculus on matrices, we're going to do calculus on warped curved things. And that's what the topic on Wednesday is going to be. So we're going to see some of the stuff we talked about today a little bit more in depth on Wednesday, but they're going to be to a little bit of a different tune. So to start things off, a group is just a set with some sort of gluing together operation. So you have a set G such that if you take any 2 elements G and H, you can glue them together in some sense that gives you back an element. They're associative, so parenthesis placement doesn't matter. There's always an identity, so there's always something that if you append it to it, nothing happens. And the last thing is inverses exist. Okay, so this seems abstract and scary until you start to think about a couple examples, and a couple examples make this a little bit less terrifying. So if there's an eraser. So the very first example of a group you ever see is if you have the integers and addition, okay? So if we look at this, according to these things, if we have 2 integers and we add them together, we get back an integer, right? The second one, if we have, integers and we add them together, it doesn't matter what order we add them in, right? If we take, 4 plus 5 plus 6, this equals 4 plus 5 plus 6, right? So nothing scary going on, right? It behaves the way you want it to behave. Of course, with the identity, what thing when under addition does nothing? 0, right? So 0 is the identity element in this case. And the last thing is the inverses. According to multiplication, what's the inverse of addition? What's the inverse of addition? Subtraction, right? So in this language, 4 inverse just equals -4. In the sense that when you take 4 and you add it to -4, you get back 0, is all this last thing is saying. Okay? And of course, the next example you always see is you have the real numbers subtract 0 and multiplication. Right? And of course, this follows everything the same as before. Because if you take 2 real numbers and you multiply them together, you get a real number. Parentheses, of course, don't matter. You can multiply things in whatever order you want. The identity element here now is going to be 1, because if you multiply something by 1, nothing happens. And the inverses here now are the usual inverses. This is going to be the reciprocals. Okay? But one other question to ask is if we have the integers and multiplication, is this thing a group? Why not? Yeah, if you have 2, right, the multiplicative inverse of 2 is a half, but a half isn't an integer. So an important thing when you deal with groups is a group is really 2 things. The group is the set, and the group is also whatever the gluing together operation is. So in this sense, the integers are a group under addition, but not multiplication. But of course, the real numbers are a group under both. Right, you can multiply them, you can add them, nothing too spooky happens. So a matrix group is just a collection of matrices that also follow these rules. So it's matrices that when you multiply them together, it follows whatever you're talking about. The order of the parentheses don't matter. There exists some sort of identity element, which is, your identity matrix, and you can, invert the matrices is all that this is saying. And we'll come back to examples of matrices that follow these rules. So, again, now we're going to get into matrices. So, M, N are going to be M by N matrices. And the K means that's what the coefficients are, because, right, a matrix is just a grid of numbers, but you got to specify what those numbers are. So, for the purposes of this class, it can be the real numbers, the complex numbers, or the quaternions. But of course, we don't care about the last two. Everything we're going to deal with are real numbers. So if you're not comfortable with complex or quaternions, we don't really care. Everything is just a real number to us. Anything else is too scary. And if you're really curious, K just has to be a commutative ring, if you know what that means. If you don't know what that means, then ignore that sentence. So the very first matrix group we're going to deal with is the general linear group. And the general linear group is just the matrices that determinant is non-zero. Because, right, if the determinant is non-zero, that means you can invert it. So that means everything follows through, right? And of course, the reason why, so on the last slide, K could be R, C, or H, but we don't care about that because the general linear group of C, we can view it as a general linear group of R, and H can be viewed as a general linear group over C, and we can just scrub everything off as just being R and forgetting about everything else. So I said C and H on this side and last slide, but just scrub those from your memory. Everything's just real numbers. Okay? So the general linear group are just square matrices of real numbers that when you take their determinant, it's non-zero. Okay? And if we go back to the group definition, if our group is the general linear group over the real numbers, right, the group operation is going to be just good old-fashioned matrix multiplication, right? If you take two non-singular matrices and you multiply them together, is this thing non-singular? Right? Because if you take the determinant right, and since we assume neither of these things were zero, the composite's not going to be zero, right? So if you take two general linear matrices and you multiply them together, you get something back, right? You have associativity, right, in the sense that it doesn't matter which direction or which order you multiply them in, right? You can multiply GH first or you can multiply HK first, it's fine. And you have inverses, of course, because since the determinant is non-zero, you can always invert this thing. So, right, recall that the determinant of the inverse is 1 over the determinant. And since we assume this thing isn't zero, we're not getting any troubles. And then, of course, the identity element in this case is just, the matrix with ones on the diagonals. So this is going to be kind of the parent Lie group we're going to talk, matrix group we're going to talk about all throughout today. And all the matrix groups we're going to deal with are going to be things that sit inside of this. This is the overarching framework we're going to deal with, are just matrices whose determinants aren't zero. So the next example we have is we have what's called the affine group. So the affine group is going to be a square thing where now what we think of is this matrix A in the upper corner is just given by something general linear, it's just whatever it is. And then this element T, which is just going to be a vector. So we can think of affine matrices as some sort of a general linear matrix and a vector paired together. And the way we think about this is you have your position in Rn, right? So again, we can think about n being 3 if you want to talk about the real world. So you have your 3 vector, you append this one at the bottom. This is called homogeneous coordinates for whatever reason. And then what happens is when you take this element, which is again your general linear matrix and your translation, it just multiplies out this way. Okay? So if you think about it, this is like your screw motion or whatever, right? Where A is going to talk about how you're rotating and T is going to talk about how you're moving. Right? And in general rotation plus translation, right, this is going to be what's called your affine group. And again, if you take all matrices of this form and you go through those 4 rules we had for groups, you're going to see that everything works out. If you multiply these two together, you're going to end up with a new affine thing, right? The order of the parentheses don't matter. There's always going to be an inverse. There's always going to be an identity, yada, yada, yada. Nothing scary happens. This is just another example. So what we can think of is we have the affine group, which is the collection of all of these matrices to define all the different ways we can move. But we also have this thing which just defines how, right, this matrix by itself defines how we move, and we define how we move by acting on a thing, right? So just this singular affine element gives us what's called an affine transformation. So another way we can think about this is the affine group is also the affine transformation. But the affine group is all of the transformations under the same roof. But a specific affine element is a specific affine transformation. And again, right, you can think of this affine transformation as a function, and then you can do function composition, and function composition works out to be another matrix group. Everything follows through, right? We're just using things under different languages, but nothing different is going on, right? And of course, the affine transformations include translation, which if it's purely translation, that means your matrix here is just going to be 1, right? And all that you have is t's happening. You can have similarity transforms, you can have reflections, rotations, shears, all this fun stuff. And we'll talk about a lot of these different specific examples further throughout this lecture. Okay, so affine is kind of, well, general linear is truly the biggest, and then affine is kind of the next biggest matrix group we're going to deal with. And of course, as we hone these down, they're going to be more useful because we can say more about them. So again, if we let the matrix A in the affine group just be the identity, we end up with what's called a translation group. And again, if you look at this thing, it's called a closed subgroup because if you just take matrices of these forms, all of these count as affine matrices, but these on their own follow those rules over there. So if you have a big group of a collection inside them that follow their own group laws are called a subgroup. Okay. Questions so far? So probably the most nifty group we're going to deal with are those of the orthogonal group. And an orthogonal group, right, is just made up of orthogonal matrices, and these are matrices that when you multiply by your transpose, you get the identity. So you probably have seen rotation matrices before. This is just all the given rotation matrices. And again, right, if you take 2 rotation matrices and you multiply them together, you end up with another multiplication or another rotation matrix. And that's what makes the rotation matrices into a group. But of course, we call them the orthogonal group because we want to call them that instead. So when we look at the orthogonal group, we have the orthogonal group is defined off the relation that A times A transpose is the identity. So we can, of course, hit the determinant on everything. And this just tells us that the determinant is equal to plus or negative 1. So the orthogonal matrices fall into 2 camps. We can either deal with the determinant equals 1 or the determinant equals negative 1. So as a quiz question, it's either of O plus or O minus by themselves a matrix group. Them together is O of n, which is a matrix group, but individually are either of them a matrix group. Yeah, is the other one? No, why is the other, okay, why is this one not a matrix group? Well, if you have 2 things from here that have determinant negative 1, and you multiply them together, what is their determinant going to be? Positive 1. Does that live in here? No, it lives up here. Remember, the rule for a group is when you do things together, it has to stay in the group. So if you take 2 things down here, they pop out up here, and that's not allowed, right? But of course, if you take 2 things in here, they stay in here. So this is its own self, a nice little group on its own, right? This isn't. So again, what we notice is when we take this orthogonal group, right, the intersection of these two decomposes is empty, right? Because something can't have both determinant +1 and -1 simultaneously. You can't really do that. So ON is just one copy of O plus and one copy of O minus, right? And they're two disjoint things floating around in space, okay? And then since, as we talked about in the last slide, O plus is by itself its own matrix group, we're gonna call that thing the special orthogonal group. So throughout everything, if you don't say special, that means the determinant can be whatever it wants. If you use the word special, that means the determinant has to be 1, okay? And in terms of actually like rotating things around, what is the difference between the special orthogonal group and I guess the negative orthogonal group? Right, so like, let's just talk about, you know, if we're in the plane, right? And so the orthogonal group is just rotating things around in the plane, right? What rotations are allowed in SO2 that are not allowed in O2 minus? Like intuitively, physically, what's special about the special orthogonal group? Well, they both are only one direction. So so if we have SO2, this is just given by you take your thing and you rotate it around, right? But if we have O2 instead, this can include reflections, right? So if you take your hand, right, this thing and this thing are the same thing under SO2, but this thing and this, my two hands together are different copies of each other, right? You can't rotate your left hand into being your right hand, and that's what this takes up. So when you're in the O minus, this corresponds to looking at the universe through a mirror. When you're in SO, this talks about normal rotations that you can physically do. So for you guys as engineers, you almost exclusively care about this because you can't really take your robot and put it through a mirror and look at like the inside out version of your robot. It's mathematically legal, but it's kind of stupid in real life. So we're really only gonna care about these, and the reason for that is we're just gonna ignore reflections. And another intuition to think about, if we take two of these things, right, we're gonna pop out up here. So if we do two reflections, nothing happens. If you look in a mirror twice, it's the same thing as not looking in a mirror at all, if you want another intuition on that. All right, so one of the main reasons that we like the orthogonal group, but of course specifically the special orthogonal group, is they are called isometries. And an isometry is something that the distance stays the same. So if you think about it, if you have your hand and you rotate it, if you have any 2 points on your hands, the distance between them after you rotate it, I mean, the hand distance isn't going to change, right? As you move these things around, distances between these points are going to stay the same. And that's entirely what this says here. When you have the distance between your 2 points and you apply an isometry to it, the distance stays the same. And again, if you think about it, if you look at yourself in a mirror, right, the distance on your face stays the same in the mirror, but of course that's not allowed by normal laws of physics. So ON is the group of is also a group of isometries, but they're kind of stupid isometries. So you kind of got to keep there's a notion of orientation as well as just measure, or not measure, but distance preservation. So you can be a little bit sloppy, but again, we really only care about special orthogonal. So another nice thing to know about is if the isometry fixes the origin, then it has to be given by something either an ON or SON. Right, you can think about it, if you take your hand and you move it to the left by 1, again, that's an isometry because no distances change, but that's not going to fix 0, and that's not going to be the same thing as matrix multiplication. That's going to be something from the translation group we talked about earlier. So, as you'll see later on, all isometries are really given by some sort of a translation and then something in an orthogonal group. So, the special orthogonal group is just rotation about these perpendicular planes. So a way you can think about it, right, is in SO2, this is just rotations of the plane. It's just turning clockwise or counterclockwise. SO3 is rotation about yaw, pitch, and roll. So a way to think about it is SO2 you can only rotate in one dimension, so it's a one-dimensional thing. In SO3, you have yaw, pitch, and roll, so you can rotate in 3 different ways, so it's 3-dimensional. As a quiz question, what is the dimension of SO4? I'll give you a hint. The pattern is 1, 3, blank. It's not 5. It's not 9. It's not 7. You'll get there eventually. It's 6. So you'll see later on, we'll do the computation for why it's 6, but it's 6, and then SO5 is 10, and then SO6 is 16. And then so on and so forth. So one of the things that's odd is you think about it, in SO3, which is the universe we live in, it's 3 dimensions, because you think about it, you have your x, your y, and your z axis. You can rotate about each of them for yaw, pitch, and roll, and that gives you your 3 different rotation directions. The trippy thing is in a 4-dimensional universe, you can actually rotate in 6 different ways, which it makes absolutely no sense why you can rotate in more ways than there are dimensions to rotate in. But this is why it's always disappointing we live in a 3-dimensional universe, because it'd be more fun if you could spin 6 ways. So, as we talked about earlier, SON are called direct isometries, and the word direct just means there's no mirroring is allowed. And while elements of ON are called indirect, because indirect just means mirroring is allowed. So again, we like talking about this distinction a lot just to make sure you guys are aware, but right, we don't want to do mirrors. But according to just the pure laws of algebra over there, the negatives are allowed too. So, as we talked about earlier, this thing of isometries, this contains all of the SON, ON garbage, and it also contains all the translations, because of course if we take one step to the left, nothing is going to get bigger or smaller. So the question now, it really is, what is this thing? I think that's what we're talking about next. Yeah. So the isometry group lives again inside the affine group because it has the same form where it's a matrix with the upper left-hand corner is a matrix, the upper right-hand corner is a vector, the bottom left-hand corner is a 0, and the bottom right-hand corner is a 1. Where now what's going on is A is an orthogonal matrix, and T, of course, is your translation. So the way you think about this is A tells you how you're turning, and T tells you how you're moving. And then basically every way you can move that doesn't change, that doesn't cause lengths to go stupid is just by some sort of a rotation, some sort of a translation. And it's a pair of the two. And we call this thing SEN for the special Euclidean group. And again, the special means we require the determinant to be 1. If you do just the Euclidean group, that allows for reflections, which allows for it to be just ON, whereas SEN requires determinant 1, which requires SON, which requires no mirroring is allowed. So we're really only going to care about SEN, but again, S just means no reflections. So a rigid motion is just something that preserves distance, right? Because if you think about it, if you deflect your thing, that means something gets closer to something else. So the whole concept of any kind of rigid motion we have is the exact same thing as talking about something being an SEN. So in particular, anything in real life that you do that isn't messing with any kind of distance is something in SE3. So whenever you talk about, the distance from like a robot manipulator to the robot base, or, you to the lab wall, or whatever it is that you're talking about, that's all described by something in the special Euclidean group. This is just kind of the abstract formalism to put everything together. So of course, all of kinematics, dynamics, and all this stuff has lots to do with rigid body things. And what we're going to do is we're going to now look at these matrix groups as opposed to, just the equations of motion or whatnot. So, a rigid body, again, is just something that is rigid, which means that, no two particles can get closer or further apart, which again really just goes back to the special Euclidean nature that you can't get closer or further away. So the only valid thing you can do with a rigid body is you can only rotate it or you can translate it. You can't shear a rigid body because then it would no longer be rigid because then you're tearing it apart. So again, a rigid motion is anything that takes this thing and preserves the fact that it's rigid. So really all this is setting up is you have your collection of points that aren't going to drift closer or further away, and the only valid thing you can do to this thing is something in the special Euclidean group. You're going to rotate it or translate it, and you're going to keep points from getting closer and points from getting further apart. So we're going to get into a little bit of terminology. Right, you guys have your body fixed frame and your inertial coordinate frame, right? So the inertial frame, right, is your lab frame or whatever you engineers call it, and the body frame is whatever, I guess, the body frame, right? But again, right, from the body to the lab, right, nothing has happened that's not rigid. So the way you go from a body fixed coordinate frame to an inertial coordinate, or yeah, from inertial to body or body to inertial is by using an SE3 matrix is the way we can write this down. So we can do these coordinate changes all using this language of matrix groups, which makes things be very, very nifty. So what we have is we have A, let's call A our inertial frame, and let's call B our body frame. So we have this nice nifty picture, and suppose what we do is we have X, Y, and Z be the coordinates of B relative to A. Right, so then out of this we can build this matrix. And according to this slide, this matrix is a rotation matrix, but why is this rotation? Why is this matrix a rotation matrix?
It's because they share an origin?
That's not enough. That means there's no translations. But that doesn't say why so remember, to be a rotation matrix, RR transpose has to be the identity. So why does RR transpose, if you build any matrix this way, why does this have to be orthogonal? It's not quite. Full rank just means the determinant's not 0. I want the determinant's 1. I mean, I want RR transpose to be the identity, which is a much stronger condition than being non-degenerate or full rank or whatever language you use. Well, okay, so let's think about this. We have these 3 vectors, x, y, and z. What do we know about these 3 vectors? They're orthogonal to each other and, well, okay, yeah, we're in R3, and they're orthogonal, we're in R3, and what's the other nice thing about these? They're all unit, right? These are orthogonal unit vectors, okay? So if we take the matrix RR transpose, there really aren't enough markers in this room. You'll see. So if we have R transpose, right, what is this matrix going to be? Right, we want this to be the identity, but what actually is it? Well, so this is going to be, right, so there's 3 columns. It's going to be X, Y, and Z times, let's write it this way, times the transpose, right? So how does matrix multiplication work? Well, that just comes from going across and down, right? So when we multiply these things throughout, this matrix is going to give us, well, the upper left-hand coordinate is going to be the dot product of x and x. And then we're going to have x dot y, and then x dot z, y dot x, y dot y, y dot z, z dot x, z dot y, and z dot z, right? And then what do we know about all these dot products? Well, what do we know about x and y? They're orthogonal, so the dot product has to be 0. X and z is, again, orthogonal, so they got to be 0. So all of these things are 0. And then we had the question about why these things had to be unit vectors, because when they're unit vectors, what does a diagonal have to be? 1. So what happens is we get the identity. Okay? So a nice thing to know about rotation matrices, if you don't know this, it's a good thing to know. If all the columns are orthogonal unit vectors, then your matrix is automatic. That corresponds to it being a rotation matrix. Likewise, any rotation matrix, all the columns are going to be orthogonal unit vectors. If it's all orthogonal unit vectors, it's rotation back and forth. Okay, so that's how we know this, change of coordinate frame is going to give us by something that's a rotation matrix. Okay. Questions about that? Yeah? What did I mess up? This matrix? Well, okay. Fine. That good? Okay. And again, right, so, okay. So again, right, just reviewing, so now we're considering ourselves in R3. So our R matrix that we do to go between coordinate frames, as we said, right, is a rotation matrix, which just means RR transpose or R transpose R is the identity, which we saw from that computation. And then, of course, we're assuming it's special, which means there's no mirroring going on, so we're assuming the determinant is 1. So we have our group of rotation matrices. This is a typo, that should be GL3. And again, now we're just only viewing on 3-dimensional things as opposed to arbitrary dimensions, so you can kind of view this. The set of SO3, which is again a matrix group on its own right, we're calling this the rotation group. Okay, so O3 and SO3, right, is again the same thing minus if you get reflected or not. But from here on out, we're going to just ignore O3 even exists. And rotation things mean SO3. Okay? And any way you can rotate around is described by something in SO3. As we saw from the last example, right? If we have any coordinate frame B and any coordinate frame A, you can relate the two with just any kind of rotation matrix. So if you say A is the one given by God and it's the greatest coordinate system ever, every single other coordinate system B is synonymous with just describing a rotation matrix. So really, orientations and such are synonymous with just being an element of SO3. And the last thing we want to talk about is a trajectory in SO3 is just a curve that lies in SO3. So here we say T is between minus epsilon and epsilon, but that's just arbitrary. It's just something where we have some kind of time domain. It really doesn't matter what it is. Just, we have some start time and some end time, and all the way in between this is something in SO3. So if you think about it, right, as your robot arm is moving and the things are rotating, at each time instance, right, it's at some different orientation, and the collection of all that trajectory together is, well, a trajectory. So again, we have our usual composite rules, which just mean that these things work the way you think they are, right? So RAB and RBC are constructed in the ways that you think they should be, just given by all of these coordinate expressions. And then the thing at the bottom says when you multiply them together, they behave the exact way you think they should, right? B in terms of A and C in terms of B, but when you compose them together, you get A in terms of C. Right, and these things cancel out, which means you can measure A and B, you can measure B and C, and that for free gives you the measurement between A and C. So, what we can think about now is if we have RAC, which again is our rotation matrix from before, we can view this as a matrix which just takes 3 vectors, you multiply them together, and you get another 3-dimensional vector. Right? But if you have these 3 numbers, what it does is your first 3 numbers are coordinates and according to C, and then your last 3 numbers you get after multiplying this matrix is going to give you coordinates in terms of A. So if you have a measurement on some robot, and you have, you know, the angles or whatnot that the robot's hand is saying according to the robot, but you don't care what the robot says, you care what the room says. What you do is you just multiply it by the matrix between the room and the robot, and that gives you everything that you need. So it's really just bookkeeping, which is the boring part. So everything we've done so far is only for the rotations. We've only dealt with the rotation matrix, but of course in real life you're allowed to do more than just rotate, you're allowed to translate as well. So what we have now is in addition to the matrix R, A, B, we also have a vector P, A, B, which tells you how much you move in what direction. So in real life, right, as your robot's moving around out, you know, exploring its life, it can both rotate on its own, which you got to keep track of, and it can also, you know, move wherever it wants. So again, we got to know this translation and rotation, and of course this thing together, this GAB, this is going to belong to the special Euclidean group, which just means it's rotation and a translation. So again, as we saw earlier, the special Euclidean group is just something that is both a translation and a rotation. And the way you think about it now is you have this element G, but G represents the pair together. It's both the translation and the rotation. That when you move by G, it's the same thing as moving along by P and then rotating by Q. Okay, so a thing to be very, very careful about, and this is kind of nitpicky, is if you translate first and rotate second, and then if you rotate first and translate second, you will get different answers. So it's very important, again, with your bookkeeping, you keep track of this. So according to this, right, formula here, do you rotate first or do you translate first? You rotate first. Right, because you think about it, you have your vector Q, right, which is where you are. You hit it with R and then you add on P. If you translate it first, it would be R times the quantity P plus Q, which again would just be a different answer you got to deal with. And ultimately, it really doesn't matter which one you do. You can either do rotations first or translations first. The only thing that's important is you're just consistent in what you're doing, right? You can do this however you want. You just got to make sure you do the same thing, because if you change what you're doing, then you're just going to get wrong answers, and that's not fun. So, as we saw here, we've kind of seen two different ways to write the special Euclidean group. So, I like this way more, but Mani, I think, likes the other way more. So I guess I have to tell you both. I still don't have a marker. Is we can think of SE3. We can either think of this as the set of translations and rotations. Or we can also think of this as something in the affine group that we showed earlier, and these are going to be matrices of this form. Okay, and a thing to keep in mind, these two are the exact same ways to do it. Right, what we're doing is here we're keeping track of everything as a 4x4 matrix. Here we're saying screw that, and we're just recording P and Q separately, or sorry, Q and P and R separately from one another. But these are both the exact same ways to do it. I prefer this way, I think Mani prefers this way. It's the exact same thing, it doesn't matter. And again, if you think about this, if you do PR, right, so your translation and your rotation, and you take your measurement Q, this is going to be P plus RQ. Whereas if you use the second way, you got to use homogeneous coordinates, and you're going to get RP01 times Q1, which is going to give you RQ plus P1, right? So when you forget the 1 at the end, you're going to get the exact same answer.
I'll throw this on out.
Oh, that's a lot better. Okay, let's rewrite this then. All right, so our two ways of viewing the special Euclidean group is we can either say SE3 is given as a pair of a matrix and a vector. Or we can view this as 4 by 4 matrices. Right, and the only difference is the bookkeeping, because if we take our P and R and act on a point Q, this is going to be P plus RQ. And if we take our matrix on Q1, we're going to get RQ plus P. You can read that better? Okay. So again, these are both completely synonymous ways of doing it. They're just kind of different bookkeeping, right? If you're doing the math of things, it works probably better this way, whereas if you're actually trying to tell MATLAB to do something, it's easier to store a 4 by 4 matrix. But again, if you're using the matrix notation, you got to remember that this one at the end is garbage, and you just got to ignore it at the end. So based off of this, it seems like we have this following thing here. So far it looks like the SE3 is equal to SO3 times R3, right? Because it's just given by a pair. It's given by a rotation matrix and a translation. And you can either record it just as this, pair of the two, or you can try to encode it as a matrix. But why is this equation wrong, or at the very least misleading? Well, if we have two things, let's say P and R, and let's say we have, Q and S. If we multiply these two things together, right? So according to multiplication is the group thing, right? Where we translate and rotate, and then we translate and rotate again. Does this thing equal P plus Q and then R times S? If you scooch some and rotate some, and you scooch some more and you rotate some more, does that equal scooching twice and rotating twice? Is this formula true? No. Right, what is the correct formula? Well, the way you can think about this correct formula is, well, you just do these matrices and you just do the matrix multiplication, right? So we can think about this as RP01 and SQ01. And when you multiply these together, you get RS, you get RQ plus P 0, 1, right? So the actual correct answer you get when you compose these is you get RQ plus P and then RS. Okay? So one of the nice things about this is the rotations do play nicely together. If you rotate some and then rotate some more, that's the same thing as rotating twice. But if you rotate and translate, then you can't just add the translations together. You have this extra term pops in. Okay? So if you want to really impress your friends, what the correct notation is, you do this. And that's called a semi-direct product, because the thing on the right's a normal subgroup. So if you want your $5 word of the day, you can say that. But again, we're not going to go into details. The main thing to keep in mind is when you do these, it's not just the same as just doing them individually. There's a little bit of this cross-play comes into terms here that you have to keep track of. So again, that's kind of what we're seeing here. A way you can view these SE3 in terms of homogeneous coordinates is when you do this thing with the 1 on the end. You view these as 4x4 matrices. So if you call it homogeneous coordinates, that means you do the big matrix thing and you have this extra 1 floating around. Where of course you don't need to do that, but of course you can. So the homogeneous coordinates of point Q just means you take Q and you turn it into a 4 vector, but the fourth coordinate is always 1. But again, now we're talking about, you have your trajectory, you have your actual path that your robot's taking through all of these motions, which means we care about our speed, which means we care about differentiating things. So if we take this homogeneous coordinate and we differentiate everything, well, we don't know what these things have to be, but the derivative of 1 always has to be 0, right? I mean, if you differentiate a constant, that's always 0. Hopefully you guys know that. So that's why when you do the homogeneous velocities, or whatever you want to call them, you have these 3 terms which correspond to how fast these 3 things are moving. But then the last term is always going to be given by a 0 because 1 never changes. So a couple rules that we're talking about. So a way to think about this here is the coordinates of a point is the actual location that you were at, whereas the vector is the velocity that you are going. So a way to think about these things is points are locations and velocities are vectors. So in terms of this, if you take the sum and difference of a vector, you can do that because the vector is velocity. You can add and subtract velocities from each other and you get back a velocity, which is a vector, right? If you take a vector and a point, that means you have a location, you add to it a movement, and you're going to end up at a new point. So a vector plus a point equals a point. The difference between 2 points, right, is going to be the distance between them, which is going to give you a velocity of some sort. So if you subtract 2 points from each other, you get a vector. But adding 2 points is garbage, right? It doesn't make sense to add 2 locations to each other. So this is a bit odd because everything we're dealing with are 4x1 vectors, but only the things that we call vectors, which are these things where the fourth coordinate is 0. These are the only things we're legally allowed to add to each other. We can add a v to a q, we can add a v to a v, but a q plus a q is stupid. And another way you can think about this is the last coordinate always has to be 0 or 1. If you take 2 of these and subtract them from each other, you're going to get the last coordinate of v, which is going to be a vector. But if you add 2 of these, your last coordinate is going to be a 2, and that's garbage. You don't do that. So I guess as a way to protect, your last digit has to be a 0 or a 1. If last digit's a 0, it's a motion. If last digit's a 1, it's a location. So if the last coordinate is 0, it is a motion. It is a velocity vector. It is what you're moving somehow. If the last coordinate is a 1, it's a physical location. And if it's anything but 0 or 1, you made a mistake. So what we do is if we have an actual element that's a 4x4, so it's the other version of SE3 that we talked about, that's called a homogeneous representation because it acts on homogeneous coordinates, which is this thing with the 0 or the 1 added at the end. So as we saw over there, right, a homogeneous so this pair is the thing in SE3 because really all SE3 is rotations and translations together. If you choose to represent them this way, that's just called the homogeneous way to do it. If you don't specify homogeneous, you can do it however you want, but if you use the words homogeneous, it's got to be done as that matrix. And again, as we see down here, the same rule applies, right? If you multiply the 2 together, the 2 rotations multiply together, but the 2 positions don't add. They have this extra weird in-between term going on. Questions? Yeah?
So not just H matrix represents a rotation, any rotation in the matrix.
Yeah. I mean, it'll be a specific ones, when we do examples and whatnot, but H is just the pair. And it's encoded as this 4x4. So all that we're saying is when we say homogeneous, we mean this notation, not this notation. Right? They're both the same, but in terms of bookkeeping, homogeneous has this extra 1 thing going on at the bottom. This would be called non-homogeneous. I don't know what you would call this top one, but homogeneous specifically means this bottom one. So again, we can do this, and remember this thing has to be a group, which means you got to be able to invert them. So homework for you guys is to understand why H inverse has this form. So again, it's straightforward enough to tell why this R is R transpose, because remember, R times R transpose is the identity. So this is going to give you the identity, but remember, this term has this extra R transpose in it. So it's your homework. I mean, it's a 30-second scribble you can do to figure out why H inverse and H inverse H has to be the identity matrix. All right. Are you guys properly confused? Because it's going to get more confusing now. So a matrix group is just a set of matrices that follow the group laws, right? It's got to, be closed under multiplication. It's got to have inverses. It's got to be associative, and it's got to have an identity element. But we can view this thing, as opposed from just these pure formulas, we can also view this thing as an actual geometric object. We can actually think about the set of all of these rotation matrices as its own geometry, and we can think about the shape of all the different possible shapes on their own, if that makes any kind of sense. So what we can think of, right, is matrices are just a grid of n by n numbers. So that's the same thing as just n squared dimensional space. So our matrix group lives inside some really large dimensional space, so it's just going to be a shape of its own right. So we can talk now about the geometry of this thing that lies inside this big. So right over there, the homogeneous coordinates was a 4x4 matrix. So our special Euclidean group lives in some 16-dimensional space, whatever it is. Okay. So again, we can talk about the geometry, but this is going to make your brains bleed because you got to think about 16-dimensional geometry for this. But I mean, in math, we can do this, right? And likewise, since we can talk about these as being shapes, we can also talk about the tangent space. So as a quick reading, if I say manifold or tangent space, does that mean anything to anyone? Okay, then you're going to be in for fun. A little bit. So this is where things are going to get a little bit hairy, but it's not very important that you understand the equations. It's more important you understand what physically is going on. So a tangent space is literally the tangent. So I mean, you guys have all taken Calc 1, I think. And you know what like a tangent is, right? It's the curve, it's the line that lies nestled above a curve, right? This is just the exact same thing, but just more abstract. So to draw a picture, just so we have a picture that's a little bit exciting to draw, suppose we have a sphere. So this is some shape living inside R3. Right? And suppose we have some kind of a curve. I got to draw this without making it look too terrible. And suppose we have some point on this curve. Okay? It makes sense to ask about the tangent, right? If we do this tangent of this curve, mathematically, what's another way to rephrase the word tangent to this curve? Starts with a D. Derivative, right? If you differentiate the curve, that's going to give you the tangent on it, right? Right? So the tangent's going to be given by this thing. So now what we do is we can ask the question of what are all the possible different tangents, right? And if we come up with every single possible curve through this point, what we're going to end up with is some sort of a plane lying on this sphere. Okay, so the tangent space on the sphere is literally you just take a plane and you nestle it on top of the sphere, right? I mean, mathematically it gets a little funky, but the fundamental idea is you just literally just take a tangent thing to it, right? If you have a three-dimensional thing, your tangent space is now going to be three-dimensional, but the construction is the same. It's really you take the curves and you look at their derivatives, which are going to be tangent vectors. You take all possible tangent vectors, that's going to give you some sort of a plane or a three-space or whatever. So that's what this definition is saying here. We have some kind of a curve, right? And we record its derivative. And all possible derivatives we have is its tangent space. So in the same sense we have the tangent space to the sphere as this plane, that the plane holds all the possible tangent vectors we could draw at that point, which comes from differentiating these curves. So tangent space is kind of like the derivative space, I suppose you could call it. Okay, and again, this is for a two-dimensional case, but when you get these larger dimensional things, the idea still holds. Your just intuition kind of just falls to crap. But again, this will be useful because we can kind of write down equations somewhat using this idea. But really what happens is it's just some sort of a flat space tied to the thing. So what we have is, right, we have our tangent space, which is going to be this flat space that's nestled against whatever our shape is of whatever sort, right? But again, if we have our matrix group, we have a very special element of our matrix group that's the identity element. If we draw the tangent space at the identity element, that thing is called the Lie algebra. You guys follow that at all? No. Let's draw another example. So let's draw a very simple example. Let's draw a circle. Okay? So if you have a circle, this is the same thing as SO2. Because if you think about it, each SO2 are just rotations in the plane. And any way you could rotate in the plane is given by some angle which you could draw in a circle. Okay? So what you do is you have some point here, let's call it 0, right? If you choose the point theta, that's going to be the same thing as rotating counterclockwise by the point theta. Okay? And again, so this is a matrix group, but we're just drawing it as a circle. This point right here is 0, which is the identity, which means if we rotate by 0, nothing happens. We can draw the tangent space to 0, which here is going to be this thing. It's just going to be the line. And this line is called the Lie algebra. Okay? So you have a matrix group. You pick the identity element that does nothing. You draw whatever the tangent space, it's either going to be a tangent line or a tangent plane or a tangent three-dimensional thing or whatever it is, right? This thing by itself is called the Lie algebra. Okay? And then the way we do it is you always use the math frac font. And then that's just the same thing as a tangent space identity. But it turns out this thing is actually very, 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 very important. And it turns out if you know what this is, you can reconstruct the whole group. But it seems a bit odd that if you know just this line, you can figure out that a whole circle came from this line. It's easy to go from circle to line, but it's a bit odd that you can go from line to circle. And we'll see a little bit about how you can do that. And again, we'll also see a little bit, if you have scarier things than just a simple circle, it's still possible to figure out and say things about the Lie algebra. But, I mean, we'll do what we can. Sorry, say that again? So, okay, so if we are in, let's say, SO3, and let's say you have the lab frame and the coordinate, or the lab frame and your inertial frame. And let's say they're currently lined up so nothing is happening. Right? The tangent space at the identity means you start off at the identity, nothing's going. And if you move a little bit, it's going to tell you, in essence, how fast you're moving. So basically, your angular velocities are what's going to live in the Lie algebra. So in the same sense that, you know, like your Euler angles belong to SO3, their derivatives, which are your angular velocities, live in the Lie algebra. If that makes sense. Well, it's the derivative of the reference space. So the Lie group, sorry, I keep saying Lie group. The matrix group, which you're going to see matrix groups and Lie groups are the same thing. Matrix groups are your positions. Your Lie algebras are really the velocities. Yeah. Probably. I don't know how this works. Monty gave me these slides, so I guess if you ask him, he'll probably give them to you. I don't see why not. Or if you talk to me after class, I can email them to you. It's not a big issue. I don't have access to Canvas, so. But of course, what you can do is if you Google Lie groups, there's like an 80-page Wikipedia article, which is a good place to start if you like Wikipedia more than me. All right, so what we have is the Lie algebra, which is this tangent space, right? If we have our matrix group, this is just going to be some subspace of all matrices. So a little subtle thing to keep track of is, remember, a general linear matrix means it's not singular. It means the determinant is not 0, right? But this thing is allowed to have determinant 0. Because the kind of way to think about it is this includes all of the speeds you can go at, right? This is your positions, this is your velocities, If you're not moving, your velocity is 0, and of course the determinant of 0 is going to be 0. So this, of course, is going to be bigger than that, and this, of course, can contain singular things. And another thing to keep track of, if we go back here, right, we have a circle, right? What is the dimension of the circle? Right? The disk, which is the filled-in circle, is two-dimensional. But when I say circle, I just mean the skin of the circle, right? And the dimension of the circle by itself is one-dimensional. And likewise, the dimension of this line is one-dimensional. On this example, the sphere, and when I say sphere, I mean just the skin of the sphere, right? Not the interior, is two-dimensional. This plane is two-dimensional. So a nice thing that we have that we see down here is the dimension of the matrix group and the dimension of the Lie algebra are always going to be the same number. So a thing to think about with this special Euclidean group, what is the dimension of the special Euclidean group? Well, let's break this down. What's the dimension of R3? 3, right? What's the dimension of SO3? How many different ways can you move in SO3? In SO3 by itself? 3, right? You have yaw, pitch, and roll, right? And you have X, Y, and Z. So if you have 3 different ways to rotate, 3 different ways to translate, this is 6-dimensional. So if we do the Lie algebra of this, that's going to be 6-dimensional as well. So whatever we do, this thing should be 6-dimensional, this thing will be 3-dimensional, and this thing will be 3-dimensional. Just to try to keep our heads a little bit on straight. All right. So the very first thing we're going to think about is if we have the general linear group, so the biggest matrix group we can think of, just anything that's not singular, right? It's Lie algebra, which is the tangent space of the identity, is going to include everything. And so we're going to ask, why does this include everything, right? Why is the tangent space of invertible matrices every single possible matrix? And if you think about this, if we go back to this dimension, or to this definition, right, the tangent space is going to be all derivatives of all curves that pass through that point. So what we're going to do is we're going to choose a curve that's the identity matrix at 0, and we're going to differentiate it. And we're going to show that we can get every single possible matrix out as some sort of a derivative. And that's going to build us our tangent space. So what we have here is we choose an arbitrary thing, an arbitrary matrix. This can be as singular as you want it to be. It doesn't matter, right? Then what you do is you take the identity element plus some translation by this. And of course, when you differentiate this curve, what's your answer going to be? Or what's the derivative of I going to be? 0. What's the derivative of something linear? Just A, right? So the derivative of this is going to be A. And likewise, when you plug in 0, what are you going to get? Not 0, not A, I, right? So this curve has slope A, and it passes through the point I. So what that says is the point A is in the Lie algebra, if all of this circular logic is making any sense at all to you guys. Right? It's perfectly fine if it doesn't. This is probably 3 semesters worth of 600 level math classes you guys have taken in an hour. So, and again, the only other subtlety we have to do is we have this curve, right, that at 0 gives us our identity element and it has slope A, but we got to, of course, make sure this thing lies in the group of all invertible matrices. Because if it's not, then it's kind of stupid. And the way you do that is you say, well, the determinant at 0 is 1. Determinant is continuous, so on a small enough interval we can't cross 0, right? If you're at 1 and you're continuous, right, you can't teleport to 0 instantly. It's got to at least take you like a couple seconds to get to 0. And in that restricted little window, you're going to be invertible everywhere, so you have a good, well-defined curve. So if all of this was Greek to you, the takeaway is the Lie algebra of all invertible matrices are all matrices. And then we can move on with our lives. The Lie algebra of all invertible matrices are all matrices. Everyone good with this? At least with the takeaway of it? Okay. The Lie algebra of all invertible matrices is all matrices. I didn't say this wasn't going to be confusing. So if that was confusing, we're going to get more confusing. So the Lie algebra of all invertible matrices is everything. What now is the Lie algebra of orthogonal matrices? So if we look at ON, right? So again, we know the answer with SO2, right? The Lie algebra is just going to be this line, right? So what's this going to be, though, in more general cases, is it's going to end up being skew, right? If you think about it, matrices that when you add the transpose is 0 means that A equals minus A transpose, which is the same thing as it being skew symmetric, right? If you transpose it and a minus pops out, that's skew. And it turns out the Lie algebra, which is the tangent space at the identity of all rotation matrices, is given by all skew matrices. So another way you can kind of think about this is if you have a path of rotations, if you differentiate that matrix, that's going to give you a skew matrix, is another way to think about it. So we'll kind of try to come back to some intuition, but first let's confuse you a little bit more. So again, we're going to use the same trick where we differentiate things. So we have, remember, if we have a curve that is a rotation matrix, if you take it times its transpose, it has to be the identity, because that's the definition of being a rotation matrix. And what we do here is we differentiate it, right, which is going to give us gamma dot times gamma transpose plus gamma times gamma transpose dot, right? When we plug in 0, we're going to just get back these terms because everything else goes away. So I guess to write this down, you have gamma of t transpose equals the identity, right? If you differentiate this, you're going to get gamma dot gamma transpose plus gamma transpose dot equals 0, right? By product rule. But again, we're looking at the identity, which means when we plug in 0, we got to get the identity here. So what we have is we have gamma dot of 0 times the identity, which I guess we'll call I, plus plus I times gamma dot transpose equals 0, which tells us that gamma dot plus gamma dot transpose equals 0. Is everyone happy enough with this line of logic? Enough? So what this tells us is, remember, this is going to be something that lies in our tangent space because this is a tangent vector, and this says it has to be a skew matrix. So what happens is, another way you can think about it is if you have a rotation and you differentiate a rotation, that's going to give you something skew, which we'll look at the cross product later, and that's entirely what the cross product is saying. So if you've seen the cross product, that's just saying a skew thing, which is just differentiating a rotation. It'll make probably more sense, but I'm not going to promise that. So what we want to do is we want to choose like a normal basis, right? So if we have SO3, that's a 3-dimensional matrix group because you have yaw, pitch, and roll. And then what we have now is with the Lie algebra, we have these skew matrices, and what we want to choose is we want to choose them this way, right? So these are skew matrices, and every other skew matrix you can cook up in 3x3 terms are going to be a sum of these three. So this is going to give you some sort of a basis of this, okay? And when you think about it, this is rotation about z, this is rotation about y, and this is rotation about x. So if any of you want to impress me, why is this rotation about z? Z is all zeros, but why is that the kicker? If you're rotating about z, does z change? So if you differentiate something that doesn't change, what answer do you get? which is why this is all 0 on the z's. Likewise, this is all 0 on the y's, because when you differentiate the y's, nothing happens, so you get zeros. This one is 0 on the x's, because when you differentiate the x's, you get 0. So another thing we can think about is, let's say, I don't really want to deal with all of this garbage because Monty likes equations and I don't like equations, and I don't think you guys either. But let's just look at this matrix down here, right? If you guys have seen rotation matrices before, what is this matrix describing in R3? So rotation, it is a rotation matrix, but what's going on in this rotation matrix? What's happening? It is rotation about y by, well, by angle t, like in radians, right? Right? Have you guys seen this type of thing before? Right, so this is a rotation matrix about y by angle t. If you take the derivative of this, right, what does cosine of t become? Minus sine. This becomes right. If we plug in 0, right, what do we get? What does the derivative of this at 0 become? 0. What does the derivative of this at 0 become? 1. This becomes, and this becomes, and then now this is why I'm not crazy, is that's entirely what this matrix is. Okay, so this is the derivative of rotating about y. And like what we could do is, if you do your matrices here the other way, right? So if you know if it's cosine minus sine, sine cosine, you take the derivative of that one, which is rotation about x, you're going to get that other matrix on the last page, and same with all these other ones. So if you've seen Euler angles before, right, just the derivative of the Euler angles gives you these three matrices as your yaw, pitch, and your roll, like angular velocities. So hopefully that should make it a little bit, maybe kind of clear why this skew thing is not total nonsense. Okay, but of course we gotta get more nonsensy. So, one of the things that is a great bane to everyone who has ever been alive is if you multiply matrices, if you do A, B, and B, A, do you get the same answer? No. So when we do this, we have to keep track of what side we multiply on. If we go on the left or if we go on the right, we're going to get different answers because you can't flip orders. So what we have here is, if we have a row vector, you can multiply the matrix on the right, and that's what this R for. R gamma means you're multiplying by gamma on the right side. Likewise, L of gamma is you're multiplying it on the left. And the reason for these transposes, right, is X is a row vector, X transpose is a column vector. A column vector can get multiplied on the left by a matrix because, right, the dimensions have to line up. So L sub blank is you just multiply it by the blank on the left side. R sub blank means you got to multiply it by on the right side. And since nature is evil, R and L are not going to be the same answers. So again, it doesn't matter which one you use, you just got to be consistent about it. And as you'll see, it doesn't matter too much. So, a nice fact that we can say for sure now is that the dimension of the special orthogonal group is given by this formula. So going back to the quiz question I asked you earlier, what is the dimension of rotation matrices in 4 dimensions? 6. Does 6 come from that formula? And now can you figure out where this formula comes from off of the computations we did earlier? Well, remember, it's all skew symmetric matrices. So now we can figure out the dimension of rotations by counting the dimensions of skew matrices. Right? So a thing we can think about before we just jump to that formula here, right? What is the diagonal on all of these skew matrices? 0, right? And right, that's the thing, that all skew matrices, they have to have a 0 diagonal. Because the diagonal doesn't change when you transpose it, but the transpose has to be the negative, and the only number that's its own negative is 0. Right? So when you have these skew matrices, the diagonal is always out. So you only have the above diagonal and the below diagonal. But again, if you have the above diagonal, the below diagonal has to be the negative of it. So if you know what's happening up here, you know what's happening everywhere. And in this case, you have a total of 3 numbers to choose from. right? In a 4x4, you're going to have, it's going to be, these are going to be the triangular numbers, right? It's going to be 3 plus another copy of 3 as the next upper triangular thing goes about, and that's how you can cook out this formula right here, right? So you have a total of n squared entries in your matrix. You throw out the diagonal, which is you throw away a copy of n, and then you only care about the upper half or the lower half, it doesn't matter, and that is why it's divisible by 2. So you have n squared minus n over 2, and that's the total number of rotations you can make. Which gives you, in 4 dimensions, you can spin about 6 different ways. All right, so to confuse you guys even more, we can now talk about the exponential. So if you guys have seen the matrix exponential before, this is absolutely the same thing as you've seen before. Right, and of course, if you've not seen the matrix exponential, if you guys have seen the Taylor series for the normal exponential, this is just a Taylor series for the normal exponential. Okay, and we define the exponential of the matrix as just plugging the matrix into the exponential of the normal Taylor series exponential for the normal exponential. Okay, and one of the nice things that we have is this thing always makes sense. For any matrix we choose, we can exponentiate and we get some sort of a matrix that makes sense out of it. So probably in your differential equations class, right, you guys have seen this, and this has been useful for integrating ODEs and whatnot. But it's going to be interesting in ways you haven't even fathomed yet. So remember, to come up with something in a tangent space, you have to have a curve, and the derivative of the curve is going to be a tangent vector, and that's how you come up with one of these things in the tangent space. So the question is there a reasonable way to make these curves that give us everything in the tangent space? Is there a systematic way, right? Is there a systematic way to come up with all of these curves that will fill out this plane when we differentiate all of them? We can kind of do this ad hoc, but is there a uniform way to do it? And the way we do this is with the exponential. It works out magically somehow. So again, what we want to do is, given anything in the Lie algebra, we want to find a curve that when we differentiate the curve, it pops out this thing in the Lie algebra. And again, we want a recipe, given this, find this curve. So we're going to use this by use of what's called a vector field. Have you guys seen vector fields before? This is just ODEs, right? So vector field, all you're thinking about is it's just some function Rm that at each point in Rm it gives you a vector on Rm. So at each point it gives you a speed in which that you're going. So this is just, you see a ball and you put hair on it and you go about your life. But a thing called an integral curve now is something that solves this ODE. So in the same way that a vector field is just drawing, putting carpet on your shape, right? Actually following the streamlines, right, is given by your integral curve. So an integral curve is just a fancy word for saying a solution to your ODE. So what we're going to do is these integral curves are going to give us these gammas up here. We're going to be able to write down these gammas as integral curves. So the proposition is this is just given by exponentiating. So if we have a Lie algebra element, we exponentiate it, that's going to give us our curve. So if we take e to the ta, that's going to give us our curve such that when we differentiate it, we're going to get back a. And the way we think about this is we just do this in terms of the normal Taylor series, right? We know the exponential is given by this. When we differentiate it, we get this out right here. But then what we notice is we can factor an a out of every single term here. When we factor an a out, we get this original term back up here. So what happens is when we differentiate our curve, an a pops out, right? But again, our original curve, when you plug 0 in for t, what answer do we get? What's e to the 0? 1. But what's 1 in terms of a matrix? It's the identity matrix, right? So with this curve, when you plug in 0, we get the identity matrix, which is where the Lie algebra is taking place at, and it gives us our velocity that we're looking for. So a very useful formula for going between this tangent space garbage and the actual locations on it is by using the exponential map. If we exponentiate matrices, we can go between the two. And of course, if you want to go the other direction, you got to take the logarithm. But of course, a matrix log is a little bit weirder of a thing to talk about. So again, what we're saying here is, remember, r sub gamma of x is we're just multiplying x on the right by the matrix gamma. And as we said, and also here, L sub gamma is multiplying on the left. And going back here, one of the nice things that happens with exponentials is you can factor the A out on both sides. Because normally it matters which order you do first when you multiply matrices, but in terms of exponentials, it commutes. Right? You can either pull the A out first or pull the A out second. So in terms, when you cook up the curves this way, it works left or it works right. They both give you the same answer in this case, which is one of the reasons why exponentials are wonderful creatures. So questions about that? We're getting close to the end, I promise you. All right. So what we can think about here is we can take our left translation. So we have our matrix group. But left translation just means you multiply on the left by this matrix. We use the word translation, but it's really it's just left multiplication. So LG just means multiply on the left by G. And the same way that this causes the points on our circle to move about, we can also move tangent vectors around by this point by using the same differentiation rules. So how does Monty word this? So the way to think about this, I guess let's go on to the next. So, yeah, so if we have our original curve here, right, remember this thing has derivative A. We translate it to the left by G. Now when we differentiate this thing at 0, what is our answer going to be? It's no longer going to be A, now it's going to be what? Not G. Right, you have a constant times an exponential. You differentiate it, what happens to the constant? Stays the same, right? Nothing scary is going on for the first time, right? You're going to get just G times A, right? So in the same way that we can multiply the actual positions by G, we can also multiply velocities by G as well, which will come in handy in a little bit. So what we have is, remember, this thing is a curve, right, that at 0, its derivative is A. If we do left translation, its derivative is going to be GA. But likewise, we could also do right translation if we wanted to instead, and this is going to have derivative AG. So derivative GA and derivative AG both make sense. It just depends upon which bookkeeping measure you use. And one of the truly, truly weird thing about this is if you use left translation, that gives you your coordinates and body frame, and if you use right translation, this gives it to you in a spatial frame. So this is a thing just to memorize. If you're feeling really, really adventurous, there's a wonderful book by Abraham and Marsden called Foundations of Mechanics, and in it is about 100 pages using like really scary topology explaining why this actually makes sense. But if you aren't super brave, you can just take my word for it. That when you use, for whatever reason, when you use left translations, that tells you things in terms of body coordinates. If you use right translations, it works better for spatial coordinates. But in terms of actually doing the math, it doesn't matter. But for your bookkeeping, it kind of does. All right. So we're nearing the end here. One of the nice things that we can have is if we have a matrix group, we can define conjugation. So in terms of before, if we have, if we want to do different coordinate changes, conjugation is the same thing as doing a coordinate change. Have you guys seen that before? So here, if G was your RAB, if you do RAB times something times RAB inverse, this takes something and you can change your coordinate frames by doing it. So you probably see examples of this at some point hidden somewhere. But really all you're doing is you're taking your matrix A and you're just surrounding it by inverses and not. And then again, what we can do is we can differentiate this, and when we differentiate this, whenever we use the words derivative, that means tangent space, and tangent space in this sense means Lie algebras. So when we differentiate it, we're going to get something on a Lie algebra. And this looks scary, but it's not. All that means is now what we're doing is we're conjugating a Lie algebra element. So before, what was going on is these were all matrices, right? G was a matrix, A is a matrix, G is another matrix. These all belong to the Lie group. Whereas when we use the word adjoint, this thing in the middle now belongs to the algebra. So basically what's going on now is both G and G inverse are going to be rotation matrices, but this B now is going to be a skew matrix. But again, you can still just multiply them together. So whenever you use the word adjoint, that really just means you're conjugating a Lie algebra element. So it sounds scarier than it is. All it is just multiplying on both sides. So a thing that's interesting is if everything commutes, then nothing happens. So what that means, if we go back here, if A and G commute with each other, that means you can flop the orders, right? So you can pull this A out, you get A, G, G inverse, and everything cancels out, and you're just going to get back A. Nothing's going to happen. So if everything is commutative, this map doesn't do anything. So when you differentiate it, if you differentiate doing nothing, then really nothing is going to happen. So that's why if your group is commutative, then the identity doesn't do anything, because conjugation doesn't do anything. So really what's going on when you take your adjoint map, if it tells you anything other than the identity, that just tells you how much things fail to commute. Just tells you how much, order matters in your procedure. If you rotate by something and then rotate by something else, it tells you how important the order of your rotations are. But you can just view it as this conjugation thing. But wait, we can even make this more annoying. We can differentiate it one more time. So before, what we did is we had this thing, and when we differentiate this element A, we got the adjoint. So we had this conjugation by something in the Lie algebra. The next step we're going to do is we're going to differentiate these outside elements. And when we do that, what we're going to get is the bracket. So here again, right, what we do is our A of t is going to be the thing, so there's going to be A of t b, A of t inverse. Now we're going to differentiate the A of t as opposed to the thing on the inside. And this is going to give us something, again, on the algebra. And what's going to be surprising is this isn't going to be too terrible looking. So if you differentiate it one more time, the bracket is just AB minus BA. So again, if the bracket equals 0, this tells you AB and BA are the same thing. If it's not 0, it tells you A, B, and B are different things. And it precisely measures how badly they commute with one another. So I guess just to keep track of everything, because it's starting to get a little hairy, is you have your Lie group G, or your matrix group G, and you have your Lie algebra. Then your adjoint with big add and then your bracket So when you do the bracket of something, both the somethings live in your algebra. When you do the adjoint of something, only one thing lives in the algebra and the other thing lives in the actual group. Okay. So something that is very, very spooky is when you do this thing, you get back a Lie algebra element. So a fun fact, or a result of this, is if A and B are skew, then AB minus BA is also skew. Okay, so when you do these bracketing elements, it stays inside whatever Lie algebra rule you had. So it's kind of magical, but it will be useful later on. So this bracket is actually very, very, very important to everything we do. And there are 4 things that make this bracket, well, a bracket. Okay, and the first thing we notice is it's linear in both terms. So if we take our A matrix and we add on, and we multiply it out and we add on more terms, you get the more terms can pop out. So if you have the sum of two things, it's just the sum of the two brackets. If you multiply it by some numbers, the numbers can just pull out. And the same thing holds true on the second coordinate as well. So it's just truly a bilinear thing. Its skew, or anti-commutative, means that if you flip the order of A and B, right, if you think about it, you're flipping this thing, you're going to have a minus pop out. So if you do AB or BA, they're going to agree up to a minus sign. And the last thing is this really, really weird thing called the Jacobi identity. And the Jacobi identity is just weird, but it's just one of the evils of the world you have to deal with. You can kind of view this thing as a derivative, as like a product rule if you squint really, really hard, but you just kind of take it as the way it works. And one of the nice things is this is called, what is it called? The Addo-Iwasawa theorem says if you're given any bracket that follows these four rules, it is a matrix thing, right? Given no matter how you define this thing, no matter what you do, no matter how abstract or arbitrary you make this, it always corresponds to some matrix thing. So matrices, like Lie algebras and matrices and this definition of the bracket really are synonymous. So that's a nice thing to keep in mind. So what we can think about here is, remember, if we go back to little SO3, so the Lie algebra of the orthogonal matrices, we have these three things that we looked at earlier, and we can compute their brackets. So again, I encourage you guys to do this, right? This is just going to be this matrix times this matrix minus this matrix times this matrix. And if you do this computation, you get G3, right? Likewise, if you bracket 2 and 3, you get 1, and if you bracket 1 and 3, you get 2. So this is just a computation that I encourage everyone to do. It takes 5 minutes. You just got to multiply some 3x3 matrices together. But it does kind of tell you that this bracket does give you something back that's the right kind of form that you're looking for. And the other nice thing to think about, this is kind of a spooky thing. If you think, so G1, this was rotations about the x-axis, right? So if we call this thing, so if we call little g1 just this vector, because right, this is just, the coordinate in the x direction, right? And likewise, g2 is rotations about y, and call little g2 the unit vector in the y direction. What happens when you take the cross product of G1 and G2? You guys don't have to try that hard. I guess the slides call it E. All right, this is going to give you what we call G3, which is in the Z direction. Right, and what happens when you bracket G1 and G2? Well, again, it's given by that slide right there, right? This is just going to be G3. So one of the spooky things about this, specifically with 3x3 rotation matrices, is this matrix bracket, this anti-commutator, whatever you want to call it over there, it's the exact same thing as the cross product. If you turn these matrices into these vectors using this usual rule, right? Skew matrices and this bracket is the exact same thing as three-dimensional vectors in the cross product. And think about it, when you do a cross product, what are you doing? Right? I mean, what's the rule that your freshman physics teacher told you about crossing G1 and G2? You start at G1, you rotate to G2, and this tells you whatever G3 is, right? Right? So you're rotating G1 into G2, and that's telling you how you're moving, right? Whereas it's the same thing as the rotation group. So really, the idea that the cross product is you're sweeping one vector into the other to pop something out really represents the fact that we're talking about the rotation group, and these rotation things and the cross products being the same thing is kind of the same. think about it. All right, so what we can think about is if we have our matrix group, and suppose our matrix group is dimension D. Remember earlier we made the comment that the Lie algebra has the same dimension as the Lie group. So Lie algebra is also going to have dimension D. The Lie algebra now is going to be some vector space. So Lie algebra is just going to be some copy of RD somehow. So what we can think of is these things are some sort of vector spaces defined upon what's going on. And our adjoint now is just going to be some kind of a map between them. So we can think of, we have our matrices, but now we can think about matrices acting on matrices. Because we can think of these both as vector spaces, and this is a matrix that acts on a vector space of matrices. So you kind of have a matrix that acts on matrices by matrices, and your brain kind of melts from inception, but I don't have anything better to say about that. So what we can think of, though, is we can make this assignment that we take our matrix and we turn this into a matrix that acts on matrices. So we can do some examples later on. It's really weird the first time you see it. I recommend trying to just read up on it. It takes probably 2 years for this to click. So moving on, what we can think about is, right, if we're thinking about real numbers, if we exponentiate x, exponentiate y, and we get the exponential of z, and these things are just numbers, what do we know about z? It's just x plus y. But of course, this is the world of matrices, and matrices are never that nice. So when does that formula hold for matrices? If you have exponential of a matrix times exponential of another matrix, when is that the exponential of the sum? When x and y commute, okay? But hope is not entirely lost when they don't commute. And this is what's called the Baker-Campbell-Hausdorff series. So again, Google this on Wikipedia or find a whole bunch of things about where this comes from. And we can write down like a Taylor series expansion for what this z has to be. But if you think about it, you have x plus y, which is what we would hope they would be, plus this other garbage. But if you think about it, if they commute, what do all the brackets have to be? 0, right? So if they commute, this big long tail has to vanish, and then z is just x plus y, which is what you want them to be, right? So the exponential of x and the exponential of y equals basically the exponential of their sum plus this error terms which measures how much they don't commute with one another. And the way you can prove this is you can just write out exponential of x and y into the big long Taylor series for the exponentials, and you can just gather terms and you just spend about a month trying to do this algebra and you can get there. Or you can be lazy and just Google it. All right. So the nice thing, because remember I said earlier that if we have our matrix group, we can draw the tangent space to it and we can go from the circle to the line very easily. But what the Campbell-Baker-Hausdorff formula tells us is we can actually go in the reverse direction, right? If we know what all of these brackets have to be, we can solve this, right? These are going to be things in our group, right? So this tells us if we have two things in our group and we multiply them together, this formula tells us what the other thing in our group needs to be. So since we know this formula, right, this formula only exists on the Lie algebra, we can figure out exactly what's going on the Lie group side. So like down here is the formulas of what's going on this line, but the exponentials are what's going on up on the circle. So if we know, so the Baker-Campbell-Hausdorff formula tells us if we know everything there is about the Lie algebra, the matrix group follows for free, which is what the Lie correspondence theorem is. Says if you know all these Lie algebras, all these collections of things with these brackets, there's a one-to-one correspondence between those and matrix groups, and you can pass between them. So if you know one, you know the other one, and vice versa. So it really doesn't matter. You can either deal with matrix groups or with Lie algebras. They really are synonymous. All right, so we're nearing the end. And this is going to become more useful actually for tomorrow, or not tomorrow, for Wednesday. So what I talked about earlier, right, is a manifold is just anything that if you zoom in enough, it looks like Euclidean space. So, right, the reason why people say the Earth is flat is because if you zoom in enough on the Earth just looks like R2, right? So all the flat earthers, they're just very sophisticated ways of saying the Earth is a manifold, is all that says, okay? So the same thing, a donut is a manifold, right? Because the torus, the donut, right, if you zoom in enough on it, it looks like R2, right? The circle, if you zoom in enough on it, it looks like a line, right? Any reasonable shape that you can possibly concoct is going to be a manifold. There's one caveat I want to talk about though, is in all of the things we're dealing with, we care about taking derivatives because we're curious about velocities. So the circle is a manifold, but the square is not going to be a manifold. And why don't we want to call the square? Yeah, because at the corners, the derivatives are going to be stupid, right? So we want to just rule out this behavior. So when I say anything you can think of as a manifold, anything that's not sharp is going to be a manifold. So the Earth is a manifold. I mean, not talking about mountaintops or whatnot, right? But anything reasonably curvy is going to be a manifold in any dimension you can think of. And just the formality says if you just zoom in enough on it and you take a small enough swath, right, you can turn it into something of Rn, which is just what a map maker does with Earth, right? They take a part of Earth, they turn it into a plane, and that's just saying the Earth is a manifold. So what we see is any matrix group that we talked about is going to end up being a manifold. Well, any matrix group modulo these stupid corners. I mean, you don't want something silly like this to happen. So as we saw, SO3 is going to be a manifold, SO2 is going to be a manifold, especially Euclidean groups can be manifolds. So we can view these things as these like geometric objects on their own right. And that's going to be a lot of what Wednesday is going to deal with. But we're going to touch on it a little bit now so we can. So a Lie group, which I've been mistakenly saying this whole class, is just the matrix groups, but now instead of assuming that they're matrices, we're just going to assume that they're a manifold. So what we do is as a Lie group is just any manifold that's also a group, whereas a matrix group is any set of matrices that's a group. So really they're basically the exact same idea, just calling it a Lie group is more, you're thinking about donuts and spheres in your heads, whereas when you say matrix groups, you're thinking more, you know, skew or orthogonal matrices and things along those lines. So as such, everything we've talked about with matrix groups carries over to Lie groups perfectly fine. The other way is a little bit shakier, but I mean, they're really the exact same idea. Just the Lie group is a more geometric way to think about things, whereas a matrix group is more of, I guess, like an analytical, you know, MATLAB-y type of way to think about things. So, right, the Lie group is just a manifold, which just means some sort of a shape that doesn't have corners that also is a group. And since matrix groups, right, we can view these inside of Rn squared as some giant thing, we can also view them, of course, as Lie groups. So one of the nice things that we have is when we kind of view, we can view these things in different ways. Because what is one of the biggest problems of when you do Euler angles with SO3? Why do Euler angles suck? Come on, you guys, someone has to know why Euler angles are terrible. Gimbal lock, right? Right, you get singularities out the wazoo, things go terrible. So one of the things that we can think about is if we view this, instead of Euler angles, if we try to view this more intrinsically as a manifold or more just as a shape, we can avoid singularities altogether. In the same way that if you do a sphere, right, in spherical coordinates, right, the North Pole and the South Pole are going to give you singularities, but those are completely artificial. So when we kind of use these things more as the manifold structure, we can kind of ignore some of them, see past some of these singularities, but just makes life a little bit better. And here are just some examples, but whatever. All right. So let's see how much we can do in 5 minutes. Monty wrote these slides, not me, so yell at him. So one of the nice things that we have is if we have a vector in R3, so we're viewing this as a column vector, we can turn this into a skew symmetric matrix. And does anyone know the normal rule to going between 3 vectors and skew matrices? Has anyone seen this before? This is a useful computational trick. And if you have the 3 vector, let's call it A, B, and C, we can turn this into a skew matrix. And the way we're thinking about this, right, this is the x direction, right? When we had a skew matrix, what was rotation about x? It was all zeros in the x places, right? And then what was the matrix for the x rotation? It was -1, 1, 0, 0, 0, 0, 0, 0, and 0, right? This was the x rotation matrix, right? But we don't have 1. What we do is we fill in the a's, right? And likewise, what do you expect happens with the b's? So the b's are going to be the y component. How do we fill in this matrix with the y's? So what was the y skew matrix? So again, the y parts, the middle column and the middle row are going to vanish, right? So what are going to go on here? B and negative B, but which one's which? Top one is B, then bottom one is minus B. And likewise, what are we going to do with C? We're going to go from minus C and C. Okay. And then what we're going to do is let's call this, if we call this thing X, this thing is going to be X. Which way does he do it? Is X caret top or X caret top. Okay. And likewise, if you want to go the other direction, if you call this skew matrix Y, this is going to be Y opposite. Okay. So if you see, thinking of this with a vector, when you put the caret top over it, it means it's a skew matrix. If you have a skew matrix and you see the dimple on it, it's going to correspond to a 3 vector. And a fun homework assignment that I'm going to give you guys is to show this. So if you take 2 skew matrices and you compute their bracket and then turn them into a vector, this is the same thing as turning them both into vectors and then taking their cross product. This is a homework assignment for you guys to fiddle with. So, returning back to class, what we see here is, right, phi is going to be a vector. So phi caret top is going to be given by a skew matrix. When we exponentiate the skew matrix, we're going to get this thing. So does anyone know the name of this formula? You get a pat on the back if you know the name. Rodriguez formula, right? So you answer the Rodriguez formula. Of course, Google, there's all sorts of pretty pictures about how this comes about. So we have the Rodriguez formula. And likewise, we can invert it, right? So in the same sense that this takes a Lie algebra element and gives us our Lie group element, we can go in the opposite direction by taking the logarithm. And then this is the formula for the logarithm just by going in the opposite direction. Okay? So these are wonderful formulas, but they should be Googled, and they take a lot of time to talk about, but they are very interesting. All right, so the last thing I want to talk about, because we're about out of time, is that of the Jacobian. So I want to write this thing down, and I want to talk about it, and then you guys can go. So say we have the exponential, let's say we have C caret top and the exponential of R caret top. Okay? So C and R are both vectors, but C caret top and R caret top are both some sort of a matrix. Okay? And again, is it true that this equals the exponential is this formula true? Remember, the answer is of course not, because we talked about this like 4 slides back, right? When you do, right, if you exponentiate two matrices, this is the same as exponential of the sum of the matrices only when these things commute with each other. So in general, this thing is not true. Okay? But what can we do? But what we do is I gotta get my orders right. This is going to be the exponential of r caret plus something. Okay? And the thing is, we can figure out what the something is. The something is not going to be c. Right? The something is going to be, well, something. So what we say is, we say this something is the left Jacobian. Okay, so the thing is, right, this is not true, but we add on this whatcha-jiggy, and right, when we add on this error term, it is going to make it true. So this thing is called the Jacobian, and what the Jacobian does is it forces this formula to be true. So what we have, right, is we can define that J of L of R is this thing that's required to make sure that this formula holds. Right, and we can also define by the right Jacobian by switching orders of everything. And in these slides, we have some of these garbage formulas for this. So what we see here is, right, is if we use that formula with the exponentials, this is what you're going to get in order to make the things line up. And then this is what happens when you invert it. So this is just a Jacobian. You can Google this again, and we are out of time. So with that, I'll see you on Wednesday and hopefully confuse you guys more.